Okay, welcome everyone. It's time to start the second talk in the afternoon session. The speaker is Professor Eric Chung, who is from the Chinese University of Hong Kong. Let me give a first short introduction. Eric Chung is a professor in Department of Mathematics in the Chinese University of Hong Kong. He obtained the PhD degree from University of California at Los Angeles. His research interests are discontinuous Galerkin methods, computational wave propagation, fluid flow in heterogeneous medium, multiscale model reduction techniques, adaptivity for multiscale problems, domain decomposition methods, and so on. He elected as SAM Fellow in 2025. Today he will talk about the adaptive multiscale model reduction using generalized multiscale finite element methods. Let's welcome.
Okay. Good afternoon. Thank you very much for the very kind introduction. And it's also my great honor to give a talk in this very big conference. So first, let me give the outline of my talk. So first, I will mention some introduction and motivation of our research. And then I will give an overview of the method that we developed. So I will talk about both the offline adaptivity and online adaptivity. And then I will mention some application. So this is the motivation of our research. So in many applications, one has to solve problems that involve heterogeneous media. For example, in porous media flow applications, we will have to solve flow equations for this type of media. And as you can see that it contains a lot of different structures. And if we apply standard numerical methods to solve these kind of problems, so you expect that your grid size needs to be very small because there is a lot of different structure in the domain. And this means that the computation will be very expensive because you will have a lot of unknowns in the discrete problem. And that's why we would like to consider some coarse grid solver in order to improve computational efficiency. And in addition to that, we will also like some type of adaptivity because as you can see that in different parts of the domain, as you can see that there may be many different structures and we may have to do different things in different parts of the domain. So that's why this is what we mean by adaptivity. So here I will give a few examples. One typical example that we consider is this two-phase flow problem. So here, this is the set of equations. And then in this set of equations, the P is the pressure and S is the saturation of the flow. And this V is the velocity of the flow. So totally there will be three unknowns that we have to solve. And you also see here in the first equation, we need to solve this elliptic equation for P. And then the second equation is a transport equation for saturation. And then the velocity is defined in this way according to the Darcy's law. So typically, for example, we may consider a domain that looks like this. And this is modeled by the parameter kappa in the equation. So this kappa will be this type of function. So you see that there's a lot of different structures. And if you look at the saturation, so here I show two images of the saturation at two different times. And you see that, so it contains a lot of different features. And we would also like to have some way to model these different features in some efficient way. Now, another example that we consider is poroelasticity. Say here, you have the U here is the displacement field. And again, P is the pressure and so on. So you have a couple system that that relate both the pressure P and the displacement U, and then the sigma function, and this epsilon U is defined in the standard way. And typically you also see that for this coupled system, the coefficients alpha and kappa, they can contain a lot of features, and then to solve this system of equations, it also require careful analysis. So in order to give some motivation of our research, and also maybe not all of you are working in this field of multiscale finite element methods. So I will give this simple example to give you some idea of what we are trying to do. So first, so let's consider this one-dimensional equation. So you have this unknown P, okay, that is defined for x between 0 and 1. And then for the boundary condition, we set P to be 0 at the two endpoints. And then try to solve P for x between 0 and 1. And basically P is the solution of this second order ODE. And then this kappa x is a given function that can be highly oscillatory. And typically what you will do is that you take this one-dimensional domain and then you put some nodal points. And then, of course, what you typically do is that you will try to approximate the solution P by some piecewise linear basis function phi. So the phi is defined like this. So at point xi, the value is 1. And then at the other nodal points, the value of phi is equal to 0. And then between any two nodal points, this is a linear function. So it's a piecewise linear basis function. So it's a standard scheme for solving this second order differential equation. Now, and then next, of course, in order to solve this problem, what you do is that you define a space VH that is the span of all these basis functions phi. Again, this means that you represent the solution in terms of a linear combination of these basis functions. So you have a space and then you try to find the approximate solution pH in this space such that this equation holds, okay? And again, this is just a standard radiational formulation for this second order equation. So you solve this equation and then at the end, again, this is what I mentioned, you write the solution pH as a linear combination of the piecewise linear basis function phi, and then the Cj are the coefficients that you need to find, okay? Because the basis is already fixed, okay? You will have to find these coefficients C, and this will give you a linear system AC equals to B that you have to solve, and C is the unknown. And of course, according to classical analysis, so what you know is that if you look at the difference between the true solution P and the approximate solution pH, and if you look at the difference in this way, and you see that this is bounded about by this quantity, and you see that on the right-hand side, you have h squared. So this h is the mass size. And then you also have a kappa max, okay? This is the maximum value of kappa. And then you also have a norm that looks like this. So you see that it contains the second derivative of the true solution. So this means that if this coefficient kappa is highly oscillatory, so you know that this norm here will be very large. If this kappa x is highly oscillatory, this is large. And also in the case if the maximum value of kappa, if this is also very large, then you basically see that this right-hand side will be very large, okay? So you will have a reasonable answer when you choose the mass size small enough, okay? So that's why this is why we say that if the solution kappa has highly oscillatory and also has high contrast, you will need a lot of flip points in order to get a very nice answer. So, and of course, one way to deal with this problem is to consider the classical homogenization. So for the same equation, and if you know that the coefficient kappa is periodic, then you can define effective constant m, that is the harmonic average of this coefficient. And then you will basically approximate the original equation by this homogenized equation. And here m is a constant. So that's why this solution, P0, will be a very smooth function. And then classical analysis shows that the difference between the original solution and this homogenized solution is small, given that this period is very small. And you observe that this epsilon is the period of this, this periodic coefficient kappa. So which means that when the oscillation becomes, when kappa is highly oscillatory, you get a homogeneous equation. And of course, this is only a case when the equation is a simple equation like this, then you are able to obtain this nice result. Now, so that's why next we would like to try to do is the following. What we are trying to do is that can we, instead of finding the original solution P, okay, so the problem is, can we find something that is more smooth compared with the original solution P, okay? So which means that instead of solving P, can we solve P0? That is the idea. So, and now if you look at the solution of this equation, okay, again, the same equation, and if this kappa, this coefficient is periodic with period that is equal to epsilon, okay? So you basically observe that when epsilon is very small, the kappa is very highly oscillatory. But if you look at the solution of this equation, so you see that it has a lot of oscillation. But as epsilon becomes very small, you still see that there is a certain structure that can be represented by a much coarser grid, okay? And you see that this curve over here is something more smooth, and it can be represented by a much coarser grid of the domain. So the question is, how do we compute this coarse part of the solution instead of finding the original solution? Okay, and of course, one way that we consider is this finite element method. And for this method, we have to decide some specialized basis function. So for the classical finite element scheme, you basically do piecewise polynomial approximations. But here we try to design something more special. So you see that, again, you also have a partition of the domain, but then you try to introduce basis functions that contain the correct oscillations, which is something like this. So you see that at a nodal point, it has value 1, and then at the other nodal point, the basis is equal to 0. And then between any two nodal points, you see that it has some oscillation. And you can form this oscillation by solving a suitable local problem. And this is what we mean, okay? So if you consider this subinterval, okay, between from xi minus 1 to xi plus 1, what you do is the following. Again, at the nodal point x1, you require the basis to be 1, and then at the other two nodal points, you require this to be 0. So this part is the same as standard finite element method. But then within each subinterval, you basically do this. You find the basis by solving the original equation like this. Again, for each of the two subintervals, you do the same thing. And then these three conditions will be used as boundary conditions for these two local problems. And then also, according to the standard analysis, if you take this kind of basis function, and then of course you represent the approximate solution as a linear combination of this kind of basis, then what you can show is that the error between the true solution, and the approximate solution is bounded by this quantity. And again, this capital H is the cost element size, which is the size of this subinterval. And keep in mind that this, the size of this interval does not need to be small, okay? Because we are not doing the standard scheme, okay? For the standard scheme, this size of this interval needs to be very small, okay? But now you don't have to do that. And of course, there's a second term here that is not nice because of this boundary condition. But of course, there are some way to improve these terms. And well, this is what I mentioned. So of course, you will define a space that is a linear combination of the bases, and then you do the standard thing. Okay. And so now, before this end of this introduction, so I try to give a relation between the phi and the cost systems. So we call that this AC equal to B is the original linear system that is from the standard finite element scheme. Okay, and keep in mind that this system is very large. Now, and what you will basically see after we apply this multiscale finite element scheme. So at the end, okay, the conclusion is that we have a linear system that looks like this. So we have a matrix AH that is a projection of the original matrix A to a space that is a combination of the multiscale bases. And then the right-hand side, of course, you also have to project the right-hand side to the same space. So again, so in conclusion, this means that by doing this type of multiscale basis approximation, what you're actually doing is that you try to project the original matrix to a much smaller space by using a suitable matrix R. And this matrix R is defined by using the multiscale basis functions. So that was the introduction. But now we try to go to the more general case. So here, before I go into the more technical details, so I just point out the main messages. So the first one is that we try to construct some suitable basis functions. But what we do is that we will consider multiple basis functions. And these basis functions are pre-computed before you solve the equations. Okay? And again, all these basis functions are computed for each cost element. Again, so before you solve this problem, you will have a cost grid of the domain. Okay? And then for each cost element, you try to pre-compute some basis functions. And in order to compute these basis functions, what we do is that we will first construct a snapshot space. And this space contains a lot of possible components of the solution. And again, because before we solve the equation, so we do not know the true solution. And this is why this snapshot space can be considered as a library of functions. Okay, you have to build a library of functions, and then within this library of functions, you try to find the solutions. So that's why one step is to do this, and then next we will construct the required basis functions. What you will do is that within this snapshot space, we try to find out what are the most important features. Okay, so we try to find out the dominant modes within the snapshot space. And in order to do this, we have to design some suitable ways to locate or to define which components are more important. And of course, after that, you also need a way to order these basis functions. Okay, so we have to know how to add these basis functions systematically. So, okay, so for polynomials, you can order these bases easily because you first have a linear function and then quadratic function and so on. But for these more general basis functions, we need some way to order these bases. Okay, which is the first one, what is the next one, and so on. So we need a way to do this. Adaptive enrichment means that if we know that some part of the solution is not good enough, we'll need some way to enrich the space, okay? And this is what we call adaptive enrichment. Now, if we have time, maybe I can also go to some machine learning idea that can also be applied in this case. So next, let me go to some more technical details of the method. Now, to be more specific, so let me discuss the main idea by looking at this equation over here. Again, this omega is a domain that can be in 2D or 3D, okay? It's a more general domain, and U is a solution, and this kappa is a heterogeneous coefficient that is given. And of course, we want to find the solution U for this PDE. And of course, if you look at the variational formulation, you of course take a suitable space V, and then you can write down the variational form like this. Okay. And of course, your numerical scheme will also be in the same form. Okay. If the V is a suitable finite dimensional space, then your scheme may also be written in a form that is similar to this. Now, and if you do the classical linear finite element, as we mentioned before, you take a suitable finite element space VH, and then you try to find the solution UH that is the solution of this equation. This is also standard method. And now, if you look at the standard analysis, you see that the error of the approximate solution is bounded above by this quantity over here. Okay. Now, here I have a few remarks. So, for highly oscillatory kappa, so we know that the H2 norm of this true solution is very large when kappa is highly oscillatory. And there's also kappa C here. This kappa C is the contrast of the coefficient, and which means that if kappa has very high contrast, this number is also large. And again, this also means that in order to get a reasonable numerical solution, you need H to be very small, and this H is your mesh size. And of course, this means that classical method may not work in this case because you need a lot of unknowns. So that's why we want to construct a way to perform this to construct reduced models. So here are the main ideas. So our goals are the following. So we want to construct a numerical scheme that is defined on a coarse grid, and the grid size capital H does not need to resolve the scales or oscillations of the coefficient kappa. And then for each coarse region, we will construct some suitable basis functions. And the next point is that for each coarse region, we need to identify a suitable number of bases. Okay, this is what we need to know. And at the end, we want to show that the error of approximation depends only on the coarse grid size. Okay, it does not depend on the fine grid size. And it is also independent of the coefficient. Okay, you see that in this final bound, it is independent of the coefficient kappa. Again, this is what I mentioned earlier. So what do you mean by model reduction? So given the original system, AU equals F, you try to find a projection of the original system in this way. And of course, this R is the matrix that we need, okay, in the discrete setting. And what is this R? R will be some type of basis, okay? Because you basically represent U in this way, okay? So which means that the columns of R will be considered as the basis, okay? And then this W will be the coordinates of the solution in the new basis, okay? So in order to do this in a good way, we have to construct a suitable set of bases. And again, here the main point, all bases will work in this way. So we need a careful way to construct these basis functions. Okay, let me, before I go into the more technical details, so this will be the overview of the method. Again, your PDE looks like this. It's a variational form. And then we try to find an approximate solution by solving this equation, okay? And of course, in this numerical scheme, there are two things that we have to define. One is VH, okay? This is the space that we find the solution, okay? We have to define a suitable space VH. And also, again, in this numerical scheme, there's also a AH over here that we have to define, okay? This is not the same as the original A, okay? So as for a numerical scheme, this AH can be different from the original bilinear form A, which means that in order to find a good scheme, there are two things we have to define: what the space, and also this equation. Okay, we have to define a suitable equation. Now, again, it's also some overview. So again, this is the main idea. So first, we construct a snapshot space, and then we use this notation V snap. And then next, what we do is that we will define a suitable local spatial problem like this. And we solve this within the snapshot space. And of course, we have to define suitable AS and MS. Okay, we solve this local spatial problem. And then what we do is that we will take the dominant modes, which are eigenfunctions correspond to the first few small eigenvalues. Okay? And then we use these dominant modes as the basis function. And it's also important to note that we do all this locally, okay? This is not a global spatial problem. And we can just do this locally for every cost region that we define. So which means that this simulation is very efficient. And again, this is the way that we define which of the components are more important, okay? Again, the snapshot space can be very large, but this is the way that we define which of the components are more important than the other. Again, here again, we order the eigenvalues from small to large, and then we take the modes to be the eigenvalues correspond to, the eigenfunctions correspond to small eigenvalues. Again, this means that we try to take the components that are more smooth, okay? Because the lambda here can be considered as the frequency, okay? Smaller lambda means that those eigenfunctions are less oscillatory. So we try to pick up those less oscillatory components from the space as our basis functions. Now, and next, this will be more technical, okay? Maybe I will not go into every detail, but here the main idea is that we first have to decompose the domain as a union of some elements, okay? We partition domain into some cells, okay? And then we just pick a scheme that looks like this, looks like this. So I don't go talk about every details, okay? Now, so next maybe I just point out how do we find the basis functions. So again, if you look at this figure on the left-hand side, so we have a domain that consists of this kind of cost elements, okay? So in this domain, you see that there will be totally 16 cost elements, okay? 16 cost elements, okay? And then for each cost element, we will need to do some computations to form the basis functions. Now, and then what we do is the following. So we next we define the basis. So what we will do is the following. So we within a cost cell K, we try to decompose this space into two components. Okay, V1 and V2. Okay, so what's V1? So V1 is all the functions for you that satisfy this equation. Okay, you can basically consider V1 to be the space that that consists of harmonic extensions, okay? This is V1, and then V2 consists of all functions that are equal to 0 on the boundary of this cell K, okay? So we can decompose the whole space into these two components. And then next we will consider some way to form the basis. Now, so first one, okay? Now, given this V1, okay? Again, this V1 is the space of all harmonic extensions, okay? So this space is still very large. And then based on our analysis, what we do is that we define a local spectral problem that looks like this. So on the left-hand side, we have this standard bilinear form. And the right-hand side is defined by this L2 inner product on the boundary of the cell K. And then for the space V2, again, this consists of all functions that are 0 on the boundary of the cell K. We can then compute the dominant modes by using this spectral problem. Again, the left-hand side is similar, but the right-hand side is L2 inner product on the cell K. So again, and then next, of course, again, we for both of these spectral problems, we can arrange the eigenvalues in this increasing order. And again, the idea is to pick up the first few eigenfunctions as basis. So again, here I just show a few figures. Now here again, this is the kappa that we use, and now basically we consider. So we look at basically the first 12 eigenfunctions for both V1 and V2. So as you see that the eigenfunction become more oscillatory, okay? So those first few eigenfunctions, they are more smooth, but then as you add more bases, they become more oscillatory, okay? And we basically aim for this more smooth component to be the basis. Again, this contains the main features of the solutions. So maybe I just go to one of the main results. So so basically, so of course, the first thing we try to show that this an error bound for this scheme, okay? And then we look at the error in terms of this energy norm. And UH is the true solution, and UMS is the solution that we compute using the scheme that we developed. And basically, this result says that the error in terms of this discrete energy norm is controlled by a few terms that is defined like this. And one key feature in this error bound is that it is related to all these eigenvalues. So which means that we obtain spectral convergence. And again, this means that it shows that as we use more basis function, so this lambda and mu, they will increase. So that's why the error will decrease according to these bounds. This one is a bit more technical. And so that was one of the error bounds. So another error bound that we consider is this a posteriori error bounds. Okay. Again, we have the same error in terms of this discrete energy norm. What we show is that it can be bounded above by the local residuals. Okay. So for the bound that we showed in the earlier slide, so we cannot compute some of the terms. Okay, if you look at this error bound here, it depends on the true solution. Okay, so that's but then in this another error bound that we show. Okay. It actually depends on some quantities that can be computed. Okay, so for example, this R over here, this R can be is basically the local residual. Okay, if you look at the definition, this R basically defined as this so by this equation, okay? So basically you take so what it is, basically you take the original equation and then you plug in the approximate solution, okay? So which means that if you plug in the true solution, this will be 0, okay? But if you plug in any approximate solution, this will be something that is not 0, okay? But the thing is that if this number is small, then you know that this UMS is good enough, okay? Again, the conclusion is that we get an upper bound that is computable, and this local residuals can be computed. And another term is this eigenvalue that you can also compute. And because of this error analysis, we can perform this adaptive enrichment because we know that the error depends on this local quantity that can be computed. And then what we can do is that we just compute all these local quantities and then try to identify some region that the solution is not good enough, and then we try to improve the solution in those localized area. And this is what we are going to do, okay? So we basically perform this type of iterations. So say at some step m, you have some space Vm, and then in the space Vm, you can compute some solution that is called Um. And once you have an approximate solution, you can compute the local residuals, and then you try to find out which part is bigger, okay? Which part has larger residuals, and then you can, and then what you can do is that you basically do so for those residuals that are large, you basically enrich the approximation space and then perform the same step again. And let me show that this iteration converges. Okay, so again, we have an iteration. Okay, and then the m here is the mth iteration. So we have an iterative procedure. But basically, it shows that we have this contraction. So if you look at the error at the m plus 1th iteration, and we compare the error at the mth iteration, then you see that the error is reduced by this factor epsilon. And this epsilon is independent of the coefficient of the equation. It only depends on some other generic parameters. But the important point is that it is independent of the coefficient. And again, this means that this type of iteration will be convergent independent of the oscillations and contrast in the coefficient. So at this point, I first show you one test case. Okay, so we consider this domain. This is copper. Okay, and the blue value is 1, and then this red value is 10 to the power 4, and this is the right-hand side f. And then we solve this elliptic equation. Now, next I show you the performance. Now, if you look at the original linear system, okay? Now, this 2.6 times 10 to the power 5 is the number of unknowns in the original linear system, okay? So you see that the original system is very large. But next, if you look at what we do over here. So on the left-hand side, if you see that we apply this adaptive enrichment. And then in the first column, this is the number of unknowns in our scheme. And you can observe that the number of unknowns are much smaller than the unknowns of the original linear system. And if you look at the percentage error in terms of L2 norm and energy norm, you see that the errors are quite reasonable, okay? So you observe that in order to get an error that is about 1.4%, you basically use this number of unknowns. Again, this is much smaller than solving the original problem. And also in this table, we compare two ways. One is the adaptive enrichment, and the other is uniform enrichment. Again, adaptive means that we only pick up some region with large error, then we add some bases. And here, uniform means that we don't care which part has bigger error. We just add bases uniformly in the whole domain. So we also see improvement. For example, for the same 1.4% energy error. So if you do adaptive scheme, you need about 3,000 unknowns. But on the other hand, if you don't care adaptivity, so you will need more unknowns, which is about 6,000 unknowns. Now, and so next, let me also go to one more topic that we call this online adaptivity. So the key point is that the offline adaptivity is sometimes not enough in some cases. Now, if you recall what we did before, so all the basis functions are computed locally within a cell K, okay? All the bases that we have are formed in this way. But in some applications, for example, like porous media flows like this, so the solutions may contain global features. For example, the solution over here, okay, can affect the solution over here, okay? Something like this. So this means that if you have basis functions that are entirely local, and again, this implies that these basis functions are not able to capture any of these global features. So that's why we need to do something more in order to capture these global effects. So again, the general idea is the same, is similar, okay? You have a space VM, and then you have some solution UM, okay? And then what you do is that you try to look at the local residuals for the current solution UM. But what we do is that so instead of using the basis functions from the library, okay, we already have a library, and all these library are formed in the offline stage. Okay, so instead of doing that, we try to construct new bases. Okay, by looking at the residual, we try to construct new bases, and then we add the bases to the space and then repeat. And again, this new basis is going to capture global effects. Now, and how do we find this new basis? And the idea is very simple. So we look at the local residual, and then we solve this equation to get a new basis phi by doing this. And then the conclusion is, let's just go to the conclusion. The conclusion is that we obtain these contraction properties. Again, if you consider the error at the iteration n+1 compared with the error at iteration m, and you see that the error is reduced by this factor over here. And this factor will be quite small, okay? As you can see from the examples. So next, I just use this example to show what we mean, okay? Again, you look at the same equation, and then this is the A that we use. Now, I just go to this table. So basically what you see is the following. Again, we do the basis function that we just mentioned. So you see that if we use, say, for example, 248 unknowns, the energy error is about 8%. But after we add some of these new basis functions, we see that the error is already reduced to 0.25%. Okay, and you see that this method is very accurate because you only use a very small number of unknowns compared to the original system, and so on. Okay, so that's why this scheme can be very useful in in cases like this. So to show this, I just point to this example. So we have this flow in perforated domain, and this is the domain, okay? It contains some perforations. And then in order to form the fine grid, this is the number of fine grid nodes. And for our coarse grid, we have about 121 coarse grid nodes. So, and then we look at the solutions, okay? On the left-hand side, this is the reference solution, okay? This is computed using a very fine computational mesh. And then in the middle, we compute a solution using our scheme without the new bases that can capture global effects. And then you see that this is what happened. And then the right-hand side is the solution that involve the new type of basis functions. And from here, you can see that basically some of the feature can be captured by this new solution. If you look at the error, so basically these are the numbers. So this is the unknown in the original system, and if you and then these are the number of unknowns in our system, and then you also observe that the error can be like 1% in L2 and 5% in energy norm when we use about 243 unknowns. Okay, and you see that this is much less than the original system. Now, next, maybe I also show a few other equations. So the first one is this Stokes flow in this perforated domains. Okay, again, this is the equation that consists of velocity u and pressure p, and this is the domain that we consider. Okay, again, this is domain that we solve this equation outside this white circles. Okay, this is domain outside the white circle. This white circle are not part of the domain. And then so for the equation, basically we have to define this equation in a suitable way. Again, we may not go into every term, but we have to write down this this equation in a suitable way. And of course, for this Stokes equation, we also need to be very careful about the mass conservation. This is also important. And then for the basis construction, this follows the same methodology that I mentioned. We first start with the snapshot space. Again, this is a library of functions. And this is how we do. So we basically consider a cost cell. Then we solve the system of equations by using suitable boundary condition. And we do this to build a library of solutions. And then next, once we have the library, and then we need a suitable special problem to perform dimensional reduction. And this is how we define the special problem. Now, so we show some examples. So basically on the left-hand side, what you see is the two components of the velocity. And this is the reference solution that are computed on a very fine computational mesh. And then this is the solution using 4 bases. And then the last column are the solution using 16 bases. And you see that the last column basically are very close to the reference solution. Of course, in order to show the convergence, we also have some theory that shows, again, for the approximation space that we have both space for pressure and velocity. Then we of course need to show some stability condition in this form, okay, for the scheme that we consider. And then we also have a convergent result that says that the error between true and approximate solution will be bounded about by a quantity that looks like this. And again, the key point is that you have this 1 over lambda, okay? So this shows that as we use more bases, lambda will increase, so 1 over lambda will decrease. And this capital H is the cost element size, okay? Of course, there are some other terms that require some definitions. But this is the convergence results. And then we have also designed this method for elastic wave propagation in heterogeneous media. Okay, so this is the equation that we consider. So U is the solution that we want to compute. And then somewhere here, there's a C here that is a elasticity tensor, that this C is a given coefficient. Again, that can be spatially heterogeneous. So again, for the scheme, we can also write down an equation that looks like this. Okay, so we solve this equation to compute the approximate solution UH, but of course, this is the equation. And for the basis function, basically, of course, here we have to be more careful, but the general idea is similar. So we have to define a suitable special problem that looks like this, and the A and M are defined this way. So maybe I don't go into much detail. So just go to the result. Okay. So what is this? This is the coefficient. Okay. So we call that we have this C in the equation, and the C is defined by these 6 figures, and you see that there will be some. So it consists of different features, and then we look at the computer solution. So on the left hand, this is the A is the reference. Okay, it can be considered as a high resolution solution. And then in the next 5 figures, we use different number of basis functions. Okay, so the conclusion is that if we use enough basis function, we can obtain an error that is quite reasonable. Okay, 5%, 4%, 2%, and you see that these solutions are very much similar to the reference. Okay, and also keep in mind that we use much less unknowns. Okay, if you look at the time, okay, in order to compute this solution, this is the time that we need. But on the other hand, if you look at this case over here, so the time is basically 1/4 of the time that you need from the original scheme. So it's 75% faster than the original scheme for one solve. If you solve the problem once, so the speed up is 75%. But usually you will need to solve the equation many times, okay? Not just one time, you may have to solve many times. So you can expect that the computational saving will be quite significant. And again, this is a similar equation, but it's defined in some fracture domain, okay? And again, the conclusion is also similar. So we obtain reasonable error like this, and with a reasonable number of unknowns. Now, and we can also extend this method to more general cases. For example, if we have a domain in this 3-dimensional region, and then the local partition can be quite general. You don't have to use square and so on. You can partition the domain in a very general way. And then in each subdomain, you can basically do what I just mentioned. You can construct some suitable basis function for each local domain, and you combine the things together. So basically, this image basically shows that And so we have a domain that contains some perforation. So it's a model of porous media. Okay, so the flow will go around these regions. Okay, and this shows the solution. I just, in a couple of minutes, I just mentioned that we can also try to use machine learning to solve. So here the main idea is that, as you can see, that the whole method depends on finding some suitable basis. But the main point is that if for more general problems, these basis functions can be difficult to find. Okay, so for linear PDEs, you can find the basis easily, but for more general equations, these basis functions may not be that easy to find. Okay, I mean you can define these basis functions in a similar way that I mentioned, but when you have to compute all these bases, it will be difficult. That's why we can try to do some training and then use machine learning. As what I just mentioned is in the previous few slides, the whole idea is that we try to build a library, and then within the library we try to pick up some important features. And you can see that this idea is quite similar to machine learning. Okay, again we try to build a library of solutions, okay, and then we pick up the correct solution. And you can also see that it is a flavor of learning. But maybe I just mentioned that what we will do is the following. So in short, what we do is that we basically try to learn this map. So if you know the solution at the time n, and if you need to compute the solution at the time n+1, okay, you need to know this process. And then we try to use machine to learn this map. Okay, and when you learn this map, so the idea is quite similar. So again, you first build all possibilities, and then you use machine to pick up those that are more important. And due to time, maybe I just mentioned that this kind of thing can also be done because, for example, when you have this more nonlinear equations, it will be difficult to find the basis. So that's why for this nonlinear map, we try to do this. But maybe I just go to this figures before I stop. So basically, this is the true solution, okay? And then in the next three figures, we show the predicted solution by the machine. And it matched quite nice with the true solution. That's the conclusion. And so here is a quick summary. So what we do is that we, again, try to solve some PDE that contain heterogeneous coefficient. And then we try to construct a small dimensional space that can approximate the original solution well. And in order to find this small dimensional space, so one way that we do is we do some learning process. Okay, we first have a library of functions, and then within the library we try to locate which of the components are more important, and then we use those dominant modes to solve the equation. And of course, this idea is problem dependent. Okay, for different. So the general concept can be applied to different equations, but when you solve one specific equation, you have to define those terms more carefully. So the precise definition, how to find the scheme, is problem dependent. For each specific problem, you have to know how to define the snapshot, local, special problem, and so on. But the general concept is the same. And with that, I would like to thank you for your attention.